Okay, guys, let's go ahead and take a look at the rest of this practice test for exam 3. We're to the problem where, unlike the last one, we have to use logarithmic differentiation on it. And it's important to understand why. It's not a polynomial function where you can just say, well, let's use the power rule on it, because it has a variable base, so power rule doesn't work. It's also not an exponential function where you can just say, let's just take the derivative of with our rule of exponential functions, because exponential functions have a constant base. This has a variable base. So we need to understand variable base, variable power. There's not a simple shortcut rule to take care of it. So we just say, well, okay, it's not a big deal. We just use logarithmic differentiation on it. And we'll go in and say, let's take the natural log of both sides of our equation. When we take the natural log of both sides of our equation, on the right, we use principles of logarithms to simplify. We can say this cosine of 5x can and should come down in front of the natural log of x. And then we'll have the natural log of y is equal to the cosine of 5x times the natural log of x. Then you can say, okay, at that point, we're ready to take the derivative. The derivative of the natural log of y, derivative of any natural log, is 1 over what's inside the natural log times the derivative of the natural of what's inside. So you get 1 over y dy dx. On the right-hand side, derivative of cosine of 5x is negative 5 sine of 5x times the second. Remember, I have to use the product rule here. So this derivative of the first times the second plus the first cosine of 5x times the derivative of the second, derivative natural log of x, 1 over x. At that point, you just say, well, now we need to solve for dy dx, and we need to solve for it solely in terms of x. So instead of just simply multiplying by y on both sides, we put what y is equal to in terms of x. Dy dx is going to equal y, which is x cosine to the 5x times this group. And what I did here to simplify this group to make it look nice, I put the second term first because it was positive and the first term was negative. So I just said, well, I could write this second term as cosine of 5x over x, and then minus 5 sine of 5x natural log of x. I put that as minus 5 natural log of x sine of 5x. Order of multiplication there doesn't really matter. I just thought that looked a little nicer. And then that's your fully factored final form of the answer. For the next one, in fact, the next 3, we get to our related rates problems. In 16, we have your classic ladder example where we have a 29-foot ladder that's resting against a vertical wall. If the bottom of the ladder is being pushed towards the wall at a constant rate of 4 feet per second, we're asked how fast is the top of the ladder moving up the wall, and the moment of that we're interested in is when the bottom of the ladder is 20 feet from the wall. So that's the point of interest of the problem, when the bottom of the ladder is 20 feet from the wall. I went ahead and drew a picture that really helps in these problems. And it also is important to label as variables whatever varies in the problem, leave as a constant whatever is not varying. So please understand here that 29-foot ladder that's leaning against the wall, I didn't call that a variable because that length is not changing throughout the problem. So the hypotenuse here, which is the length of the ladder, 29 feet, it's going to stay 29 feet throughout the problem. However, that distance that the base of the ladder is from the wall that we're interested in at the moment of interest, it's 20 feet. But we know it's being pushed towards the wall at a rate of 4 feet per second. So that horizontal distance is changing. I'll call it x. Anything that varies must have a variable. Now, it didn't mention what the height of the ladder up the wall was, so we'll just go ahead and call that y. First thing you need to do is solve for y. It's a simple Pythagorean triangle. So you can say, well, we know that x squared plus y squared should equal 29 squared. And we know x squared is 20 plus y squared is 29 squared. That would give you y squared would equal 29 squared minus 20 squared. Thus, y is the square root of 29 squared minus 20 squared. That gives me the square root of 441, which is 21. This is one of our what we call Pythagorean triples. So the height up the wall at the point of interest is 21 feet up the wall. Now, what we're asking though is how fast that height is changing if the base is being pushed towards the wall at 4 feet per second. So in order to find that, I go back to my Pythagorean theorem, x squared plus y squared is 29 squared. And instead of plugging in my values for x and y, this time I want to take the derivative in order to be able to solve for dx dt and dy dt. Okay, so the derivative of x squared, 2x dx dt, derivative of y squared, 2y dy dt. We know the derivative of any constant on the right-hand side, 0. So, and again, whenever you're thinking about it, that right-hand side is the square of the length of the ladder. So even if you called that z squared and then the derivative 2z dz dt, you would need to understand that dz dt in this problem is 0. The length of the ladder is not changing. So whether you put a variable there or not, you should be able to understand, okay, the right-hand side is 0 when I take the derivative. On the left, from this step to this step, in addition to plugging in the variables, I went ahead and just divided both sides by 2. 99% of the time you can do that in these problems. So I can say, well, if I divide by 2 on both sides, those just disappear. 0 divided by 2 is still 0. So then in plugging in, the x value, x at the point of interest is 20. dx dt, please be careful there. A lot of students will mess up and say, oh, dx dt is 4 because it says it's being pushed towards the wall at a rate of 4 feet per second. You're probably not going to be given the negative sign. You have to understand that in relation to the length of x. You say, well, as that ladder is being pushed towards the wall at a rate of 4 feet per second, we have to understand that that 20 feet length is decreasing at the point of interest. It's not going to increase in another second. It's going to go from 20 to 16 to 12, excuse me, on down until it's against the wall. So dx dt has to be a negative 4. It's decreasing in length by 4 feet per second. Now, plus the y value here, 21, times dy dt, which is what we're solving for, has to equal 0. In order to solve for dy dt, you could move the 20 times negative 4 to the right-hand side. When you do, it's going to become a positive 80. And then you would divide by the coefficient of dy dt, 21. So my exact answer here would be 80 over 21 feet per second, which as a decimal approximation, you can say, well, if the ladder is being pushed towards the wall at a rate of 4 feet per second, then that means the ladder is going up the wall at a rate of approximately 3.81 feet per second at this instant in time. All right, next question. In it, I tell you that car A is 50 miles west of car B. Car A is traveling east at 70 miles per hour. Car B is traveling south at 40 miles per hour. Find out how fast the distance between the cars is changing after 24 minutes. Okay, so in this problem, first thing I did is I drew up the initial conditions, the original position of A, original position of B. I know they're 50 miles apart. Now, what I went ahead and did though was I said, well, let's figure out where the ending position of A would be. So I went over here and I said, A is going to travel, or A travels. We know A is traveling at a rate of 70 miles per hour for 24 minutes. So that's 70 miles per hour times the portion of an hour, 24 over 60. That's the same thing as 70 times 0.4. 70 times 0.4 is going to be 28. A has traveled 28 miles. Now, it's extremely important that I label my picture correctly. The distance that A has traveled from the original position is 28 miles, but that means that the ending position of A is still 50 minus 28, or 22 miles short of the original position of B. So A is still 22 miles west of the original position of B. Now, the B at the point of interest, you can say, well, at the same time A is traveling, B is traveling south. And we know that B is going to travel at a rate of 40 miles per hour, again, for 24 minutes. When you multiply that out, you'll get 16 miles. So B is 16 miles south of its original position. So I can say, all right, then I'm looking for how fast they're changing whenever A is 22 miles west of the original position of B, and B is 16 miles beyond or south of the original position that it was. And I could find the distance at the point of interest by calling that distance z. And it does need a variable because that distance, every distance in this problem is going to be changing. So if I went in there and I said, well, z squared is just the hypotenuse of your triangle here with legs of 22 and 16, then you know that z squared is going to be the square root of this side squared plus this side squared. And it's best if you just keep that a nice exact value. Since the square root of 740 is an irrational, I'll just leave it the square root of 740 there. Now I go back into my problem, and that same Pythagorean theorem that you can use to solve for z will enable you to find dz dt. So I go ahead and I put the Pythagorean theorem, and again, remember, anything that varies must stay a variable before you take the derivative. Every variable is varying in this problem. So I'll say, all right, x squared plus y squared is z squared. I take the derivative, I get 2x dx dt plus 2y dy dt equals 2z dz dt. Now, just like I did in the previous problem, from this step to this step, I said, you can just ignore the 2's. You can here too. If you divide both sides by 2, we just get the x dx dt plus y dy dt equals z dz dt. Now you plug in what you know, x at the point of interest. And please be careful here. X is not 28. X is the length within the triangle that you use to determine the distance of z. X is 22. And again, you also have to be thinking about dx dt. It said that A is traveling east at a rate of 70 miles per hour. Well, you can't call dx dt a positive 70. It has to be a negative 70 because x at the point of interest will be losing distance, not gaining distance. So since x is decreasing, dx dt has to be negative. So negative 70 there. Plus the length y is 16, and 16 is going to be increasing in distance by 40 miles per hour. So that's a positive 40 there, equals z, the square root is 740, figured that out up here, times dz dt, which is our goal of the problem. Now, in order to solve for dz dt, I just went ahead and calculated 22 times negative 70 plus 16 times 40. I got negative 900. Divided by that by the square root of 740. This would be my exact answer. Type that into your calculator. You'll get the decimal approximation of 30 or negative 33.085. And that's, of course, in miles per hour. So we know in this case that the distance is decreasing at a rate of 33.085 miles per hour. For 18 here, we have the problem in which we have a rocket that's traveling vertically at a speed of 1,200 kilometers per hour. The rocket is tracked through a telescope by an observer located 25 kilometers from the launching pad. We're supposed to find the rate at which the angle between the telescope and the ground is increasing 4 minutes after liftoff. Okay. So in order to do this problem, I'm thinking, well, all right, I'll go in here, draw my picture. We have our drawing in the triangle where the vertical side is going to be the rocket going up in the air. The horizontal side is that the person is trying to track the rocket with an angle that's rotating up as the rocket goes up in the air, and they're located 25 kilometers from the base of the rocket. Now, the goal in this problem is to find out what d theta dt is, as this theta has to increase as the rocket goes up in the air. First thing I went ahead and did is I had to find out what y was at the point of interest. I know that the rocket is going up by 1,200 kilometers per hour, but we're interested in the instant where it's how fast the angle is increasing 4 minutes after liftoff. So the position of y at the point of interest is just going to be 1,200 times 4 over 60, or that's 1/15 of an hour. 1,200 divided by 15 is going to give you 80. So I can say, okay, at the point of interest, the rocket is 80 kilometers up in the air, and we know that we're 25 kilometers from the base of where the rocket is. So then I can say, well, all right, I could also find out how fast the hypotenuse, the distance that this angle is from where the rocket is at any point, the distance diagonally, and you could just say that's your hypotenuse, and that'd be the square root of 25 squared plus 80 squared. When you do that, you're going to get the 7,025 there inside the square root, of course, to solve for z. Now, in order to solve for the angle theta, you have to be careful. Sine and cosine do not work in this problem. You think, why don't sine and cosine work? Because sine and cosine are both going to use the hypotenuse in their formula. Adjacent over hypotenuse for cosine, opposite over hypotenuse for sine. The problem with that is I don't have a clue how fast this distance, the diagonal distance, is changing. However, I do know how fast the vertical distance is changing, and I know that the horizontal distance is not changing at all. So since I know dy dt and I know dx dt is equal to 0, I need to use the tangent function because it's going to give me the ratio of opposite over adjacent. Yes. So I say, all right, the tangent of theta is equal to, and remember, before you take the derivative, anything that varies needs a variable. So tangent of theta equals opposite over adjacent. Tangent of theta equals y over 25. So we can't say 80 over 25. You have to say y over 25. Now, this adjacent side did not need to be called x because it's not changing in the problem. It's a constant. I would prefer to think of that as 1/25 y on the right-hand side. That enables me to take the derivative pretty easily. Derivative of tangent is secant squared. So I get tangent of theta is secant squared theta times the derivative of the angle d theta dt. On the right, I would just have 1/25 dy dt. Now, a lot of people would struggle to where this comes from, but what it's coming from is, of course, that secant squared theta. We know that secant is the reciprocal of cosine. So then you're supposed to go back and remember, okay, cosine is the ratio of adjacent over hypotenuse. So that means secant has to be the reciprocal of that ratio, and it has to be hypotenuse over adjacent. So if I said, what is the secant of theta here? You'd say, well, it's hypotenuse over adjacent. It's the square root of 7,025 over 25. So the inside is the secant of theta. We had secant theta quantity squared. I square the group. So this is secant squared theta in my problem. We're solving for d theta dt. On the right-hand side, I have 1/25 times dy dt. We already know that's the rate at which the rocket's going up, your 1,200 kilometers per hour. Now, that's going to give me d theta dt. When I took 1,200 divided by 25, I got 48. And in order to get d theta dt by itself, I went ahead and multiplied by the reciprocal of this fraction on both sides. That's why you'll see 25 squared in the numerator, 625, the square root squared in the denominator, just to give you 7,025. 48 times this fraction gave me 4.27046 approximately. And now it's important to understand the default answer you get anytime you're working one of these problems and you're trying to solve for an angle, the angle will be by default in radians, not degrees. And the unit of time measure in this problem was in hours. So this is kind of a quite unuseful answer of, hey, it's increasing by 4.27046 radians per hour. When most people want an answer, and I'll try to make sure on your test that I say, please put your answer in degrees per second, You say, well, okay, that gives me a little bit better idea of what's happening in the problem, how fast it's increasing in degrees per second. All that you have to do is unit conversion here. So our answer was in radians per hour. If I want to get rid of radians, then I need to divide by pi radians and multiply by the equivalency of 180 degrees. So you say, well, that's just multiplying by an understood one. You'll get degrees, you'll get rid of radians. Now, in the same manner, I need to multiply by 1 hour to get rid of this 1 hour, and then divide by the equivalent of 1 hour in terms of seconds. So you'd say, well, we know there's 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is going to be 3,600. So I'll multiply by 1 over 3,600 to convert to seconds. So once you do this, the 4.27046 times 180 over pi times 1 over 3,600, you're going to get the final answer of 0.068 rounded. And that answer is going to be a nice answer in degrees per second. Okay, up next, we're to the problems where we're looking at estimating with differentials. And you can say, well, if I'm supposed to estimate the change in y using differentials, and I give you y is this square root function, the square root of 2x minus 7, and you're told a is 6, please remember, a is just the value of x that you're interested in the problem. So the x value of interest is 6, and we're interested in how fast the y is changing as x goes from 6 to 6.02. We're supposed to then find the error in the percentage error. So I think what makes sense to do in this problem is go ahead and find the exact answer as close as possible with your calculator. And I'll step away just a second to go grab my calculator to show you this on the calculator. Yeah, here we go. This is just a basic TI-83. Everyone should at least have a calculator this good. So when I try this on the calculator, I can say, well, all right, I'll go to my page to show you what I was putting in here. And I said, the actual change in the y values here, it's just the function evaluated at a plus delta x minus the function evaluated at a. In this problem, that's the change in the y value, f of 6.02 minus f of 6. Well, in this problem, f of 6.02, if you plug that in, 2 times 6.02, that'd give you 12.04 minus 7 on the inside. That's the square root of 5.04. And then in the second one, f of 6 would just be 12 minus 7. It'd be the square root of 5. Simplifying this, we get the square root of 5.04 close minus the square root of 5. And that's going to give us the 0.089264546. Now, that is as close as the calculator can get. Of course, since that's an irrational number, it's technically not exact, but it's as exact as we can get without using, anything more fancy than our calculator. So it'll be good enough. Now, up next, I want the derivative approximation or the differential approximation of this. In order to do that, of course, we take the derivative of our function, derivative of the square root. I think of that as the group to the 1/2 power. When I take the derivative, the 1/2 comes down in front, times the group to the negative 1/2, times the derivative of the inside 2. Now, this factor of 1/2 and this factor of 2 cancel, but then I would have 2x minus 7 to the negative 1/2 power, which means you have the square root of 2x minus 7 to the first in the denominator. The numerator trivially is a factor of 1. So I can say, all right, then this tells me that the derivative here, dy dx, is equal to this. Now I need to solve for dy, which means dy is going to equal the derivative 1 over the square root of 2x minus 7 times dx. You're just moving that dx over to this side. Now, this means the infinitesimally small change in y is equal to my derivative function times the infinitesimally small change in x. That is an equation. But now if I want to use that equation as an approximation, I can say it's only an exact equation as long as x is approaching 0 and the change in y is approaching 0. Well, what if they're not numbers approaching 0? You can still say, well, it's still probably approximately true that the change in y is equal to my derivative times the change in x. Now let's use that to approximate my function for the change in y. So the change in y should equal x at the point of interest. That's plugging in the value 6 here. You'd get the square root of 2 times 6 minus 7. That's 12 minus 7. That's where the square root of 5 came in. All I did is I plugged a in for x there. And your denominator is going to be the square root of 5 now times delta x. Delta x in this problem, 0.02. So now I can use my calculator to find this differential approximation. 1 divided by the square root of 5, and then we're multiplying that by 0.02. And you see the value that I got here for the differential approximation, the 0.0089442719. Now, the error is always the absolute value of the difference between what the exact value is supposed to be and what the derivative approximation is telling you it is. So it really doesn't matter the order of that since you're taking an absolute value. But in this case, I'll just go ahead and leave this term in there since I already have it in my calculator. And I'll say, well, the error is going to be the absolute value of this minus the exact value. So I'll say, just keep the answer I have. I just hit minus and it automatically brings up that answer. And then I say minus the 0.0089264546. Oops, if I type it incorrectly, 264546. There we go. No, sorry guys. Hard to see the calculator and look at the computer screen at the same time. 0.008926 and then 4546. Ha. Now, this, I need you to write this answer correctly. Please don't give me the scientific notation that the calculator is giving you. You need to understand that this means that there are 5 zeros before the first number you see here, and that's including the 0 to the left of the decimal place. So I just went ahead and said, okay, it's 0.0000, 5 zeros, and then 178, 1731. Now, that is the error, and it's already positive, so I didn't have to worry about changing the sign or anything. For the percentage error, I have to take the error that I just found, divide it by what the actual exact value is supposed to be, and again, make sure you take an absolute value of that to make sure you don't have any negatives in your answer. Multiply that quotient by 100% to change it to a percentage. So now, if I show you that on the calculator, I can say, well, okay, I take that error that I just found and I'll just hit divide, so where it automatically pulls it in there. And yet again, I'll say, well, I'm going to divide that by 0.0089264546. And when I do, I get this value, and I can say, oh, but I haven't multiplied it by 100%. So you can either just say all you have to do is move the decimal place 2 places or times 100 to change to a percentage. And then this tells you that the percentage error for this approximation, it's less than 0.2%. I'll call it 0.1996% error in this case. So way less than a 1% error, less than a 0.2% error. Now, for the next problem, it's similar. We're still in that section 4.1 where we're looking at approximations. In this one, it's asking us to find the linearization, which is the linear approximation of the natural log function at x equals 3. So this is find the line that best approximates the natural log of x when x is equal to 3. This is really the same thing as saying find the equation of the tangent line when x is 3, excuse me there. But you can say, well, okay, in order to do that, we can go ahead and say my linearization formula is every single time the linearization of x of this function is going to be the function evaluated at the point of interest plus the derivative evaluated at the point of interest times x minus the x value of interest. That'll give me my linear function. Now, it's pretty easy to plug into this one. You can just say, well, g of 3 is just going to be the natural log at 3. That's what I did right here. I evaluated the function at 3 to get ln 3. I need to find what g prime of 3 is. So I took the derivative. G prime of x is 1 over x. So we know that the derivative evaluated at 3 is just going to be 1 over 3. Believe it or not, that's all you have to do. You just say, okay, therefore, the linear approximation of the natural log of x is g of 3, natural log of 3, plus g prime of 3, that's 1/3, times x minus 3. Final answer there. Could you distribute the 1/3 and put it into slope-intercept form? You could. I'd actually prefer it like this, though, so I'll say final answer. The next one for 21, this moves into section 4.2, where it talks about Rolle's theorem. And remember, Rolle's theorem says that if a function on an interval starts and ends at the same place, it says if f of a and f of b are equal to one another, then you know that there has to be some point c in between a and b where the derivative is equal to 0. All right. So in order to verify Rolle's theorem for any function on any interval, you have to first show me that the function has the same y value at the beginning point and at the end point. So I did that in this problem. I plugged in f of 0 and f of 3, and I showed that f of 0 is 4 and that f of 3 was 4. So now what Rolle's theorem guarantees you is that there has to be a derivative equal to 0 for some value of x equals c belonging to the values between 0 and 3. So I just need to find that. Then I come down here, I take the derivative of my function, which is just going to give me 3x squared minus 9, just simple power rule. I take that derivative, set it equal to 0. When I do, I can say, well, if I set that equal to 0, then 3x squared is equal to 9. Divide by 3, that gives you x squared is equal to 3. Now, normally, whenever you solve out a quadratic like this and you take the square root of both sides, you would say x is equal to the positive or negative square root of 3. In this case, the negative square root of 3 is not in the range that you're interested in, or I should say not in the domain that you're interested in, so it's irrelevant. And I just said, well, x equals the root of 3 is like 1.732. That is certainly within the domain of 0 to 3 of interest here. So come down here and said this verifies Rolle's theorem. Since x equals the root of 3 belongs to the set of numbers between 0 and 3, and we know that the derivative evaluated at the root of 3 is 0, that's precisely what Rolle's theorem is saying. Thus, Rolle's theorem is verified. Next problem, and quite honestly, I didn't really care for this problem on the practice test for this one. I pulled it out of the book, but the reason I don't like it is the critical points. There were no critical points between 0 and 5, but you really do need to go through the process of trying to solve for them because more than likely you will have critical points to test. This is the type of problem where you're supposed to say, if I'm looking for any maximum or minimum on a closed interval, then the maximum or minimum could be at the beginning point or the end point or at any critical point within. So the first step, as I said, well, okay, I'll go ahead and try to find my critical points. In this case, I took the derivative using the quotient rule. I went ahead and squared that denominator, so the square root became just the group to the first power, brought the square root up to the numerator times the derivative of the numerator, minus the numerator. All of this is the derivative of the denominator. And then I rewrote it to simplify it here. And I said, the problem with this that makes it hard to deal with is that fraction in the second term. So I wanted to get rid of it. I didn't like the variables in the denominator, so I multiplied by the square root of 1 plus x cubed over the square root of 1 plus x cubed. When I did that, that square root of 1 plus x cubed distributed to the first term in the numerator and just gave me the group 1 plus x cubed. When I multiplied it into the second term in the numerator, it just gave me minus 3x over 2. I multiplied that in the denominator, and I got the group 1 plus x cubed to the 3 over 2. Now, in trying to simplify this, I thought, well, all right, all I need to do is figure out when that quotient is equal to 0. A fraction quotient is only equal to 0 when the numerator equals 0. Denominator can't make it equal 0. So I didn't need to worry about the whole thing. I just looked at the numerator and said, well, is it possible to set that numerator equal to 0? I looked at it graphically and I just said, well, if I tried to graph this out, it gave me this graph right here. And I know that it is not ever equal to 0 for any number between 0 and 5. Its only root was at negative 1.476. It wasn't possible to easily come up with an algebraic solution, so I depended upon my calculator, but unfortunately, there were no roots in the region anyway. So that just said, okay, then that just means that there's no critical point between your beginning point and end point. Thus, this is the trivial case where you can only test for extreme values at your beginning and ending. So I went in and I said, well, I can still do the extreme value theorem. I test the beginning point and end point into the original function. When I plug a 0 in, of course, I get a 0 because the numerator is 0. When I plug a 5 in, I got 0.445. So we have a maximum at the ordered pair 5.445 and a minimum at the ordered pair 0, 0. Now, again, please keep in mind, if the function had had a critical point between 0 and 5, it would have had to be included in this extreme value theorem values to plug in over here, just like the bunches of homework problems that we worked. This problem just didn't work like a lot of our homework problems, and that's okay. We're going to have exceptions where sometimes the critical point isn't in the region, and it's possible you'll have one like that on the test, but it's much more likely it'll be like your homework problems where you'll have to test the endpoints and the critical point within those to search for the maximum and minimum values. The last problem here, I'm asking you to find a cubic equation that has a given maximum and minimum value. Now, this is certainly a calculator problem because we have to simplify our matrices on our calculator. But before we get to that, let's go ahead and go through the logic of this problem. We know that the general equation of any cubic can be, well, some number a times x cubed plus some number b times x squared plus c times x plus d. Now, if that's the general equation of any cubic, then the derivative of any cubic equation is going to be 3ax squared plus 2bx plus c. Simple power rule there. Now, the fact that I have an ordered pair 1, 9 as a maximum tells me if I plug an x value of 1 into the original function, I have to get a y value of 9. So that's what I did. Ordered pair 1, 9, if I plug 1 into the original function, when I plug 1 into the original function, I get a times, remember, you're replacing x with 1, a times 1 cubed plus b times 1 squared plus c times 1 plus d. That just gives you a plus b plus c plus d. We already know the answer has to be 9. The y value when you plug in x is 9. Now, the fact that it's a maximum tells you that the derivative at that point has to be 0 because it's going to flatten off at any maximum value. So that gives me yet another equation. I can say then if I plug 1 into the derivative, the answer has to be 0. Plug 1 into the derivative, I get 3a times 1 squared plus 2b times 1 plus c. That just gives me 3a plus 2b plus c. Again, set equal to 0 since the derivative has to be 0 there. Now, for the minimum, I do the same thing. I know f evaluated at 4 has to be -8. That gives me a times 4 cubed plus b times 4 squared plus c times 4 plus d. All of those in there will give me 64a plus 16b plus 4c plus d. The answer has to be -8 in the original function when you plug a 4 in for x. Now, since that's a minimum value, again, we know the function has to flatten out when x is 4, so its derivative has to be 0. So if I plug 4 into the derivative equation, you would get 3a times 4 squared plus 2b times 4 plus the c value. That's going to give you 3a times 16, which is 48a, plus 8b plus c equal to the derivative, which we absolutely know must be 0. Now, from these 4 equations, I can set up a matrix in order to solve this out. The matrix is going to have a row for every one of the equation. It's going to have a column for every one of the variables and a column for the solutions. The first row, you just put everything in, all of the coefficients and the solutions, ignoring the variables. So the first row is going to be 1, 1, 1, 1, and a solution of 9. Second row, 3, 2, 1, 0, 0. Third row, 64, 16, 4, 1, -8. Fourth row, 48, 8, 1, 0, and 0. So you can see that the first column represents A, second column represents B, third column C, fourth column D, fifth and final column solutions. Now, what I've done is what's called an augmented matrix. It just separates the coefficients of the variables from the solutions. You don't have to do the augment. I just think it helps make it a little neater so you can see, okay, all of these are coefficients of variables. These are my solutions. Now, the goal, whenever you put this matrix in what's called row reduced echelon form, is it's going to transform all of these coefficients of the variables, and it's going to solve for it and give you 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And if you think, well, how does that help? Because then it gives you an equation, 1a is equal to this answer, 1b is equal to this answer, 1c is equal to this answer, and 1d is equal to this answer. Let's make sure to see how the calculator can help with that. So the first thing I want to do is enter this equation into the calculator. I'll go second matrix, and I'll arrow over to edit to enter in matrix A. The first thing it's going to ask you whenever you go into edit is, what is the dimension of matrix A? It's always the number of rows by the number of columns. This is a 4 by 5 matrix, so 4 by 5. Now, as soon as I do that, it's going to allow me to enter it in. So I just go to my matrix. It's 1, 1, 1, 9. So 1, 1, 1, 1, and 9 for the first row. Second row, 3, 2, 1, 0, and 0. Third row, we have 64, 16, 4, 1, and -8. Of course, I'm hitting enter after every term I'm entering in. 48, 8, 1, 0, and 0. Whoops, not double 0. All right, now, just to make 100% certain, all I did is I hit second quit to get off the matrix menu when I thought I was done. Just to double check that I do have it entered in correctly, though, I can bring the matrix A to the home screen. So I have 1, 1, 1, 9, 3, 2, 1, 0, 0, 64, 16, 4, 1, -8, 4, 8, 1, 0, 0. I'm 100% sure it's entered in correctly. Now, I want to do the row reduced echelon form of that matrix. So I go back to the matrix menu, second matrix. You're going to arrow over to matrix math, and then it's quicker if you arrow up. You're searching for that RREF right here. Row reduced echelon form of matrix A, second matrix, you have to enter in on A. Now, if I hit enter, it should bring it up. Now, this is the ugly answer. So I would prefer to see the fractions that I have listed here. So all you have to do, as you probably know, to convert decimals to fraction is hit math, enter, enter. Math, enter, change to fraction. Yes, please change that answer to a fraction. And you get it. So what it's telling me here is that the first one here, I'll get A is 34 over 27. B is negative 85 over 9. C is 136 over 9. D is 56 over 27. So I can say, okay, and you can scroll over just to make sure that that's all the ones that you need in there. Some calculators, you may have to scroll down because it might put the fractions vertically as opposed to diagonally. So you may have to scroll down, but any way you need to scroll, it will enable you to see all of the solutions. So at that point, then I can say, okay, this tells me that the only function in existence that has the specific maximum and minimum value is this function. Remember, this is your coefficient of x cubed, coefficient of x squared, coefficient of x, and the constant. And then when in doubt, you could graph it out and say, well, I don't know if I buy this. First of all, you should, but secondly, it's easy to check. If I go in here and say, well, then I should be able to type in 34 over 27 times x raised to the third. And then I'll say minus 85 over 9, and we have x squared. Up next, we have plus 136 over 9x. And then lastly, we have plus 56 over 27. And then I can say, okay, I believe I have it entered in okay. I'll hit zoom 6. I'm looking for a maximum at 1,9 and a minimum at 4,8. If I hit trace, this high point up here better be 1,9. Gorgeousness, it is. That minimum better be 4, -8. Trace 4. And I'm down there at 4, -8. That is great. So this is our final problem for this practice test. Please do remember, while you have 23 problems, I'll grade it as if there's 22. So you could make as high as 105. Since some of these problems, particularly this last one, it's a little tricky, but hopefully you also find it challenging and fun, or challenging in a fun way, not challenging in a frustrating way. Let me know if you have any questions. As always, I'll be glad to help.